All right, this is quiz number 4 for Physics 101, 3T, Fall 13. First, consider a child who is swinging as she reaches the lowest point in her swing. So I have this child, lowest point in her swing. She's going back and forth, back and forth. I want to know which of these describes the tension in the string. So I have some forces here. I have the tension, and then I also have the weight. I know from Newton's second law that the sum of the forces Ft minus Fw, that's equal to the mass times the acceleration. The acceleration is v squared over r. So the tension then equals Fw plus mv squared over r. So with that in mind, let's look at these. The tension is equal to the centripetal force. Well, this is the centripetal force. The tension is definitely not equal to that. The tension is less than the weight. Actually, the tension is bigger than the weight because of this expression, which is c, and the tension equals mass times acceleration. That's not true either. All right, rigid object rotating with angular speed omega less than 0. So say this is my rigid object. I have an omega in the negative direction. That's the clockwise direction. The object is speeding up. That means that alpha is in the same direction, which is clockwise. Negative alpha, which is clockwise. If it's speeding up, the velocity and acceleration are in the same direction. Disk is rotating at 3 revolutions per second. What is it in degrees per second? So 3. Oh, excuse me, not 2 pi. We're looking for degrees here. And in 1 revolution, there are 360 degrees. So it's 3 times 360, which is 1,000, keeping 1 sig fig, 1,000 degrees per second. Potter's wheel moves from rest to an angular speed of 10 revolutions per second. In 20 seconds, find its angular acceleration revolutions per second squared. Okay, so I have omega naught equals 0, omega final equals 10 revolutions per second. T is equal to 20 seconds, and so I'm looking for alpha. It's going to be 10 minus 0 over 20. Which is 0.5. That is A for number 4. Alright, boy swings a 2-kilogram stone in a horizontal circle. So it's like the boy is swinging this over his head, not in a vertical circle, but a horizontal circle. The string breaks when the stone rotates at 2 radians per second. Now, in this horizontal circle, the tension is the centripetal force. It's not a component of the tension. It's not combined with the weight as with the swing, but it's the tension alone that always acts as the centripetal force. So I can say then that the tension equals mv squared over r. Now, I know a few things. I know the mass is 2 kilograms. I know the radius is 2 meters. And that omega, when it breaks, is 2 radians per second. Okay, so a couple things I can do here. I can either solve for v, which is omega r. I'll do it this way. V is omega r, so that's going to be 4 meters per second. That gives me my tension, which is going to be 2 kilograms times 4 meters per second squared over 2 meters. It's going to be 16 newtons. So that's the answer. The alternate way to do this, I sort of did this anyway when I substituted, is to use our alternate expression for Ft, which is m omega squared r, which would be 2 kilograms, 2 radians per second squared times 2 meters, which also gives us 16. When traveling around a banked curve, which of these forces provides a centripetal force? Alright, if I have a car traveling around a banked curve, the centripetal force is provided, usually if it's just on a flat surface, it's the static friction. And in this case, I do have some component of the static friction, that's the x component, but I also have a component of the normal force, the x component of the normal force. Right, so it's going to be the normal force provides the centripetal force as well as the friction, so that is B for number 6. Fan blade initially at rest rotates with a constant acceleration. What is the time interval required to reach this displacement? So omega naught equals 0. It's at rest. I know that theta equals omega naught t. Omega naught goes to 0, so I have 4.2. I solve this for t. 8.4 over 0.025. The root of that. I get 18 seconds. 18.3 or 18 seconds. That is B. For number 7. Consider a point on a spinning wheel rotating with alpha equals 0. That means the angular acceleration is 0. That means that it has a constant omega. Omega is not changing. Which of these statements best describes the linear velocity? So not omega, but I'm looking for the vector v, the velocity. The linear velocity is the same as the angular velocity. We know that's not true because actually the linear velocity is related by the radius in that way. The linear velocity is changing constantly. Okay, that is true. It's not changing magnitude because it has a constant speed, but it's changing direction. Okay? And hence, that's why it's accelerating, because it's changing direction. The linear velocity... Oh, so its angular acceleration is 0, but its centripetal acceleration is bigger than 0. So it is accelerating even though its angular acceleration is 0. The linear velocity equals alpha. So that doesn't make any sense. And the linear velocity does not change. Okay, that's not true because it changes direction. Imagine you are a figure skater spinning as in this figure. Estimate your moments of inertia. So I consider myself to be a cylinder. As we did in class, let's say that the radius of that cylinder is 0.3 meters or 30 centimeters. And let's say that the mass of that cylinder is 100 kilograms. And we'll say that the height, actually let's say we don't need the height, that's all we need. Because the moment of inertia for a disk or for a cylinder is 1/2 mr squared. So that's 1/2 of 100 kilograms times 0.3 meters squared. So 50 times 0.3. And so that's 5 kilogram meters squared. And these are all pretty high values for both the radius and the mass. 100 kilogram person, that's a big guy. I mean, that's a 6 foot or taller guy. That's a big guy. 100 kilograms, and 30 centimeters is actually a pretty broad-shouldered person too. So 5, which was the lowest value given, that's actually a pretty high value for the moment of inertia. All right. Consider this figure of a rod rotating about the axis labeled C. The mass of the rod is 3 kilograms. What is the net torque? Okay, so I just want to know the net torque is rotating about this point. This torque is 0 because it's at R. Because it's at R equals 0. This torque is also 0 because theta equals 180, and the sine of 180 is 0. So I just have this force, all right? And this is let's see, what is this, a clockwise? So this torque is equal to negative 20 newtons. That's 2 meters. Is 40 newton meters. And it's in the negative. It's clockwise, so it's negative. 40 newton meters clockwise. So that was problem number 10. B. For the previous question, what is the magnitude of the angular acceleration of the bar? Okay, well, I know that my torque, what did I say it was? 40 newton meters. Now I want to know alpha. Well, alpha is our torque over my moment of inertia. Moment of inertia is 1/12 mv squared. That's 1/12 of the mass, which is 3 kilograms times 4 meters squared. That's 1/12 of 3 times 16 is 48. So that's equal to 4 kilogram meters squared. That's my moment of inertia. So I have my torque, so it's 40 Newton meters over 4 kilogram meters squared. That's 10 radians per second squared. So B is the right answer for number 11, which is the moment of inertia for this. So I have collection of particles. I is sum of mr squared. That's going to be 1 kilogram times 1 meter squared. But notice, look, I have 2 of those, so I'm just going to multiply this times 2, plus 4 kilograms times 2 meters squared. So let's see, that's 2 plus 16 is 18 kilogram meters squared. So number 12 should be D. 12 is D. This figure shows 3 levers of the same length. Each holds up a block of mass M. List the 3 levers in the order of the force required from greatest to least. Okay, the one that requires the greatest force is this one. So this is the greatest. And the one that, because I have a little bitty moment arm here, and so, you know, my torques are going to be balanced. Fr will equal that. On this side, R2 is big, so that makes F small. Over here, on this side, R1 is small. That means F is going to be really big. You probably know this sort of intuitively, but it's because you've all used levers of some sort. So that's the one with the greatest force. The one with the smallest force, the greatest mechanical advantage, as we would say, is this one. All right, so it's going to be 2, 1, 3 is our answer. 2 is the biggest, 3 is the smallest, and 1 is in between. So number 13 is C. Which of the following systems is not in rotational equilibrium? To be in rotational equilibrium, it means sum of the torques equals 0. That would mean alpha would equal 0. Ball spinning in place at a constant angular velocity. Okay, that is in rotational equilibrium, so it's not that one. Okay, this one, she is spinning faster and faster, so alpha is greater than 0, so that's our answer. And both of these have alpha equal to 0, so they are in rotational equilibrium. So the answer for number 14 is B. These 4 wrenches have forces of the same magnitude applied to them in the direction of the arrow. Which experiences the greatest torque and which one experiences the least torque? All right, the one with the greatest torque is the one that's most perpendicular at the largest R. So 3, given that force, since it's a perpendicular force, at the full length of the moment arm is the largest torque that you could get out of this situation given a force F. So 3 is the biggest. So that gets rid of B. So it's either 2 or 4 that has the least torque. All right, 2 and 4 both have forces that are at an angle, appears to be the same angle, but 4 has a much smaller moment arm. So 4 then has the least torque. So that would be D. For number 15 is D. All right, this figure shows a human arm, rotates about 0.0, gives the length there. I want to know what is the force that the bicep must exert. This came from an old test, actually. I think I just copied and pasted it. I have a force here. Actually, let's redraw it. I have my axis of rotation is there. I have a force here, and I want to know what that force here is. I have 50 newtons over here. This distance is 0.03, and this distance is 0.35. So I say F times 0.03 equals 50 times 0.35. So F equals 50.35. Pretty big value. (583 newtons, or 580 newtons. That is B, number 16. Number 17, what are the units of moment of inertia? Well, a moment of inertia is mr squared, so that's kilogram meter squared. Ventilation fan has a moment of inertia of 0.034. the torque is 0.11 Newton meters. Starts from rest, omega naught equals 0. What kinetic energy will it have 8 seconds later? And the kinetic energy equals 1/2 I omega squared. So I need to know what omega is. To do that, I first need to find alpha. Using those values, I get 0.3. And then I can find omega. I need 2.4 radians per second. Now that I have omega, I can come back over here and find out what is my kinetic energy. That's going to be 1/2 of I, which is 0.034, times omega squared, which is 2.4 squared. I get 0.097. Let's see, I must have made a mistake here. Let's see, yeah, my mistake was up here. This is incorrect. My torque was, I did the inverse of this, so it's 0.11 over 0.034. 0.11, that gives me 3.2. Let me erase some of this stuff. Sorry about this. Alright, now I find omega, which is going to be 0 plus 3.2 times my time, which was 8. I get 26 radians per second. And now I put it in over here. 1/2 of my moment of inertia, 0.034, times 26 squared. I get 11. So C. What number was that? Number 18 should be C. Alright, number 19. Rotational inertia of a disk is 0.7. When 2 kilogram weight is added to its rim, 0.4 meters from the axis, the rotational inertia becomes what? So I have this. It has a moment of inertia equal to 0.7. But then I add a mass out here, which is going to be 0.4 meters. It has 2 kilograms. So it contributes its own moment of inertia, which is mr squared. It's going to be 2 kilograms times 0.4 meters squared. .32. But then I need to add that to my original 0.7, so that's 1.02, or A, which is 1. So I say 0.7 plus 0.32, which is equal to 1. Number 19 then is A. All right, number 20, a 1 kilogram ball is attached to a string that's 2 meters long. The ball spins at a constant angular speed of 4 revolutions per second. And then you lengthen the string to 4 meters without applying any additional torque. What is the new angular speed of the ball? So this is a moment, or excuse me, an angular momentum. So I initial, omega initial, equals I final, omega final. I initial is just going to be mr squared. That's going to be 1 kilogram times 2 meters squared, which is equal to 4. And then I final is going to equal 1 kilogram times 4 meters squared, which is going to be 16. All right, so I have 4 times omega initial, which is 4 revolutions per second, is equal to 16 times omega final. So that's 16 over 16. So omega final, it slows down to 1 revolution per second. So D is the right answer. for number 20. And now finally, number 21. 10-kilogram cylinder rolls without slipping on a rough surface at an instant when its center of gravity has a speed of 10 meters per second. Determine the rotational kinetic energy about its center of gravity. So, I need to know its kinetic energy. I want to know its the rotational kinetic energy. That's 1/2 I omega squared. This is a cylinder, so it's going to be 1/2 mr squared. I only have a v, so I need to express omega in terms of v. I know that v is equal to omega r, so omega then is equal to v over r, and that's squared. My radii cancel there, so I'm left with 1/4 mv squared, which is 1/4 of 10 kilograms, that's my mass, times 10 meters per second squared. It's 1/4,000, which is 250. So number 21 is B. Alright, that is quiz 4. Probably going to take one of these questions out to make it an even 20 questions. But maybe not, I haven't decided.